Greetings to all of you esteemed professionals and industry experts. Today, I'm excited to present details about a CFD simulation of a reformer unit for one of the largest steel companies in the country, arguably the largest steel producer here. This high-level simulation was carried out in collaboration with Tofan Nida Engineering for mechanical engineering and fluid solid analysis, alongside Sharif University of Technology, which took charge of the metallurgical analysis section. This project is a perfect example of advanced simulation capabilities that can help optimize industrial processes, reduce operational risks, and enhance efficiency in large-scale manufacturing environments. If you are involved in energy-intensive industries or working on complex thermal systems like reformers, this simulation process could provide valuable insights into improving performance and ensuring the long-term durability of critical systems. This CFD simulates on critical aspects such as fluid flow analysis, thermal performance, chemical reaction modeling, and the flame behavior of reformer burners. These areas were thoroughly examined to optimize the reformer's efficiency and ensure safe, effective operation. For industries dealing with high-temperature processes such as steel production or hydrogen production, understanding the dynamics of these processes is essential. This simulation provides insights into how heat and chemical reactions interact within the reformer system, offering practical solutions to enhance process optimization and safety measures. The reformer unit is an exceptionally large furnace, featuring around 468 tubes, each filled with a catalyst that accelerates the essential chemical reactions for hydrogen gas production. Numerous burners are tasked with heating the reformer to maintain the high temperatures necessary for optimal performance. For industries involved in hydrogen production, steel manufacturing, or similar high-temperature processes, this CFD simulation plays a crucial role in improving burner efficiency and heat distribution. It ensures that the chemical reactions and energy transfer within the system are optimized, contributing to higher productivity and energy savings. The reformer operates at extremely high temperatures, reaching up to 1,000 degrees Celsius, and is subject to significant thermal and mechanical stresses. The reformer unit itself is roughly the size of a small football field, making the analysis of its performance and durability crucial. Our team at Tofan Nida Engineering conducted an in-depth simulation to evaluate the stresses within the tubes, focusing on how these stresses impact the remaining lifespan of the equipment. In high-temperature environments like this, assessing the structural integrity and long-term reliability of critical components is essential for minimizing maintenance costs and ensuring the continuous and efficient operation of the reformer. We will now review parts of the simulation report to highlight key findings and insights from this detailed analysis. The simulation model encompasses both the tubes and the interior space of the reformer. It analyzes the thermodynamic and mechanical properties of the gases, including the input gases and elements from the reformer's burners. This includes a comprehensive evaluation of thermal radiation, the metallic body, and insulation properties, with all these factors being fed as inputs to the simulation software. The simulation further involves the calculation of fuel and airflow to the burners, as well as the combustion process, allowing for precise measurement of the input elements and exhaust gases exiting through the chimney. A key part of the analysis is the evaluation of gas temperature and pressure inside the tubes, which are important for assessing the chemical reaction rates that take place at high temperatures within the reformer. These reactions, such as hydrogen and methane combustion, are fundamental to the reforming process. The properties of thermal expansion, stress, and mechanical strength of the tubes were also modeled, providing insights into the structural integrity of the system under various operating conditions. The simulation also calculates the creep behavior and remaining lifespan of the tubes under different thermal stresses. For industries focused on maximizing operational efficiency while ensuring the long-term durability of critical components, this simulation is an indispensable tool. Finally, the simulation results in the temperature distribution, stress levels, and the thermal behavior of the reformer under various conditions. These results are crucial for optimizing the reformer design and operational protocols, which can lead to significant improvements in both performance and cost effectiveness. At Tofan Nida Engineering, we specialize in providing these high-level simulations, ensuring the optimal functioning of industrial systems. Should you require our engineering services to enhance the performance and reliability of your operations, feel free to reach out to us. Thank you for your attention.